carrying on with the moles topic, I'm going to deal with empirical formula and calculations from data. Normally the data they give you is about masses. So they might say it's made of carbon, hydrogen, oxygen, and it's like 26% carbon by mass, 12% hydrogen by mass, and the remainder is oxygen by mass. And what you have to do is to calculate by mass how much of the elements are present. When you know the mass is present, then you've got to work that up to an empirical formula. So let's start with what empirical formula actually means. So there's about 4 or 5 different types of formulae you need to know. An empirical formula is like the ratio of the atoms of each element present in that compound. So water, for example, H2O, the 2 means H2, there's twice as many atoms of hydrogen as oxygen. So the ratio 2 to 1, whole number ratio. That's what empirical formula means. Let's just run through one hydrocarbon. One hydrocarbon, CH2O. If that is an empirical formula, that CH2O, if that's an empirical formula, it tells you the ratio of carbons to hydrogens to oxygens is 1 to 2 to 1. So for every 1 carbon, there'll be double the number of hydrogens, and there would be the equivalent number of oxygens as the carbon. Empirical formula, quite simple. They're just the simplest whole number ratio. And that's what a lot of these calculations ask for. They ask for calculate the empirical formula. And that's what we're trying to calculate. But some of these moles questions ask for molecular formula. So while we're here, let's go through all the different types of formulae. And molecular formula is the actual, it's the actual number of atoms of each element present in a molecule. So empirical formula talks about the whole compound. Molecular formula talks about one molecule. Remember what a molecule was? A collection of atoms covalently bonded together. So the molecular formula is how many atoms are covalently bonded together to give you that little group of atoms covalently bonded together, which we can call a molecule. And the definition is the actual number of atoms of each element present in a molecule of the compound. And if you've got the same chemical, and that's the empirical formula, then the molecular formula must always be a multiple. It must be like 1 lot of empirical formula, or 2 lots of empirical formula, or 3 lots of empirical formula, or 27 lots of empirical formula. It has to be a whole number multiple. And that's what that point is going on about. The molecular formula is always a multiple of the empirical formula. When you start doing questions, this point is quite simple, that you've worked out an empirical formula and you've got to ask yourselves, the molecule, is it 1 lot of that or 2 lots of that? And you need to know molecular mass of the molecules for you to work that out. And we'll do some examples once I've been through these definitions of what these formulae mean. So what's structural formula? Well, structural formula tells you how the atoms are arranged inside the molecule. But for structural formula, you don't have to draw every single covalent bond in. For example, if I write ethanoic acid as CH3COOH, if you know a little bit of organic chemistry, then it tells you you've got a carbon at the beginning, you've got a carbon, 3 hydrogens, and then a carbon double bond oxygen, single bond oxygen bond hydrogen. and you know the structure from looking at the way that I've written that CH3COOH. But the final formula, the displayed formula, that tells you every covalent bond, because you have to draw it in. For it to be a displayed formula, every covalent bond is drawn in, and that's the molecule. 1 carbon, 3 hydrogens, 1 carbon, double bond, oxygen bond, hydrogen. That is the displayed formula for ethanoic acid. So let's run through them again. Empirical formula, that's just a ratio of atoms present. Molecular formula is the actual atoms of every element present in each molecule. Structural formula tells you how the atoms are arranged inside the molecules, and displayed formula tells you really clearly by drawing every covalent bond in how all the atoms are arranged. Let's go to moles questions. Once you understand what the different formulae mean, and then you'll understand the question. If you don't know what the different formulae mean, people faff around with working out something they think is empirical formula, and it's not. It's because they don't understand empirical formula. So learn what I've just taught you about the different types of formulae, and then we're ready to attempt moles problem. And the moles problem in a question is presented to you normally by giving you data about the masses of every element present. And sometimes they give you percentages. The percentages question is a little bit harder than the masses question, but only a teeny weeny bit harder. I'll show you that it's almost the same. If you follow my standard method, and I am of the firm opinion that you must do this kind of calculation in the form of a table, and having drawn a table, you logically get to the empirical formula, and I'll show you how. And from that, you've got to use your common sense and know that molecular formula is a whole number multiple of any empirical formula given. And look at that last sentence there. I want to reiterate, you must do it in the form of a table. So let's get our pens out, let's get our lines drawn. We want a table. Well, what kind of table do we draw? Like this. In my example, I had carbon, hydrogen, oxygen. Element X, element Y, element Z. Now they can give you, copper sulfate would have copper, sulfur, oxygen. Any compound they choose, you're going to have to work out what elements are present. And having got that, then you do this form of table. And I want to run through it. If you're given percentages, and you put the percentages into the right box, how do you turn percentages to grams? Well, you do this very simple logical idea that you consider 100 grams. If you consider 100 grams of the compound, then if you know the percentages, you just get that many grams. So say, for example, I've got some examples here. You had P percent, Q percent, R percent. They're percentages. Well, if you consider 100 grams, like every 100 grams of this, then P grams will be the mass of P present. Q grams will be the mass of Q present. R grams will be the mass of R present in that 100 grams that you are considering. So consider 100 grams, and automatically your numbers are percentages, they become masses. Now, we want the final answer like this. X, A, Y, B, and Z, C, those A, B, and C, they're not masses. They are the number of atoms or the number of moles. They're a ratio. The ratio of atoms will be identical to the ratio of moles, etc. So we want to turn these grams that second line down, you've got grams. We want to turn the grams into moles. And the way we do that is we need the periodic table. You look up the atomic mass. You look at the atomic mass of X, the atomic mass of Y, the atomic mass of Z, and then you divide the mass by the atomic mass. So P divided by the atomic mass of X. Q divided by the atomic mass of Y. Z grams divided by the atomic mass of Z. And once you do that on your calculator, then you'll get some decimals in this stage here. You get some decimals. When you've got the decimals, we need to work them up to whole numbers. And the easiest way to do that is to divide by the smallest. If you divide by the smallest one of these, then that smallest one, when you divide by itself, will be the number 1. So when you divide by the smallest, one of these will be the number 1, and that will be a whole number. It may be that the others are whole numbers too. So when we say divide by the smallest, you divide them all by the smallest. Divide all 3 by the smallest. And that keeps the ratio. If the ratio's 3 to 6 to 9, if you divide by 3, you get 1 to 2 to 3. The ratios are preserved when you divide all the numbers by the same number. So don't worry, the division by the smallest, divide them all by the smallest, that will still keep the ratio correct and it will not mess it up. And finally, sometimes you need to scale up. So you might get an answer here, 1, 2, and 2.5. Well, then the answer would be 2, 4, 5. I'm trying to multiply everything by 2 in my head. So 1, 2, 2.5, they're not whole numbers. So double everything, and then there will be whole numbers. 2, 4, 5. And therefore you get x2, y4, z5. Anyway, look. As I explain my table, and I want you to pause the video, note the headings here, get your mind around the headings. They are the headings I want you to use on any empirical formula calculation. And it's not just empirical formula calculation I want done in the form of a table. I want water of crystallization done in the form of a table too, which we will do, and I'll show you how to do that in another video. So let's do a real example. This real example here. Example 1. Oxalic acid comprises means it's made up 2.22% hydrogen. That's by mass. When it says that, it means by mass, and it means roughly. These don't have to be spot on. They're normally experimental data and they are almost spot on. But don't let the fact that they're a little bit out confuse you, as you'll see. 26.6% carbon by mass and the remainder is oxygen. Calculate the empirical formula. Standard question. Now, some of my pupils get stumped just on what are the percentages. Well, the percentages are these two. They go in there. Element, hydrogen, carbon, oxygen, they go in there. But you're only given 2 of them. You've got 3 elements, but only 2 percentages. Well, you know what? There are only 3 elements present. It tells you the remainder is oxygen. Therefore, you do 100. Take away 2.22%, take away 26.6%, and that's the remainder, that's the oxygen. So the oxygen will be 100, take away those percentages. Watch. These are percentages, hydrogen, carbon. Now, we want the elements there, we want that to be oxygen. There, oxygen. 100, take away those percentages, gives you 71.8% oxygen. So you need all the percentages. So that's telling you that if you've got masses, the masses in terms of percentage terms are attributable to carbon, hydrogen, oxygen as per those percentages. But we don't want percentages. We can't do an empirical formula. We can't do an empirical formula that is percentages driven. They're moles driven. The small numbers are ratios of moles or ratios of particles or ratios of atoms. They're not driven in terms of ratios of percentages. So we have to do the next step. Consider 100 grams. Well, believe it or not, for every 100 grams, 2.22 grams will be hydrogen, 26.6 grams will be carbon, 71.8 grams will be oxygen. Can you see they're just the same numbers? They're just now grams because you've considered 100 grams of that compound. And then, how do you turn them into moles? Well, you divide by the atomic masses. Look, atomic mass of hydrogen on a periodic table, the number 1. 2.22 divided by 1, 2.22 is the answer in terms of moles. Carbon, 26.6 divided by 12, 2.216. That is moles of carbon. Same with oxygen. Look it up on a periodic table. The atomic mass is 16, and you divide 71.8 by the atomic mass of 16, you get 4.4875. So that's that step. They're the ratios. That is H 2.22, carbon 2.216, oxygen 4.4875. But empirical formula is a whole number ratio. So how do we work that out up to a whole number ratio? Remember me whispering on about divide by the smallest? That's the smallest. No, actually, that's the smallest. 2.216 is the smallest. So divide them all. Divide that by 2.216. Divide that by 2.216. Divide that by 2.216. I've divided by 2.22, thinking that was the smallest. So it's a mistake on my part, but, 2.216 and 2.22 are almost the same. So the answers you come out with are 1, and that's 1 and 2. And I said to you that a lot of the time the data given is not spot on. And that's why my error didn't faze me. I didn't think I'd made an error. But when I tell you to divide by the smallest, 2.216 is a teeny weeny bit smaller than 2.22. Do it. Divide them not by 2.22 like I have done. Divide by 2.216. Then you'll get the number 1 here. This will be a little bit bigger than 1. And that one will be a little bit bigger than 2. But then we round them and we get 1, 1, 2. And the empirical formula is therefore C1, H1, O2. And therefore the empirical formula, we don't need the 1s. If you need to put 1 in, then in mathematics, like in chemistry, you don't need to put the number 1 in. And therefore you just write CHO2. That's the empirical formula. There you go. That laying out of the calculation like that, logical, stepwise, learn the headings in this column. That's how you're going to do them, and that's how you'll get them right and get all the marks. Another example. Now, a lot of the time they ask you about hydrocarbons, carbon, hydrogen, oxygen, like I've done. This one is zinc, carbon and oxygen. Zinc, carbon and oxygen. So here you're given the grams to begin with. You're not given percentages. So percentages given, you can just leave those blank and start here. Start in the second row, which is about masses. So zinc, carbon, oxygen. Leave out the percentages because you're given masses. Can you see how the masses question will be a little bit easier. Could you put 1.3 grams of zinc straight in? Zinc, carbon 0.24, oxygen 0.96. You're given those, you put those in, that they are the masses. Right, now, how do we turn the masses into moles? Well, you divide by the relative atomic mass. The relative atomic mass of zinc is 65. So you divide by that 1.3 by 65. Carbon, the relative atomic mass is 12. Divide that by 12. Zinc, the relative atomic mass is, no, not zinc. Oxygen, the third element, oxygen, I looked at the Z there. The oxygen is 0.96 grams. You divide by 16. And when you do the calculation on your calculator, you get 0.02, 0.02, 0.06. Work that out to whole numbers. Divide by the smallest. 0.02, you get the number 1, 1 and 3. You don't need to scale up because they're whole numbers already. And therefore the answer is ZnCO3. Zinc, C, carbon, O3, zinc carbonate. See, the method always works. I want you to use this method. Right, example 3. Calculate the empirical formula of a hydrocarbon. Mass is 85.7% carbon. And now here, they want you to use the molecular mass is 28. And they want the molecular formula as well as the empirical formula. So this is a little bit harder, but it's simple enough. You just follow the table. You put the carbon, hydrogen, and there are only 2 elements. If there's only 2 elements present, you don't need that last column. This is a hydrocarbon. Hydrocarbons only have hydrogen and carbon only. So if they've got those only, you don't need that last column. These are the percentages. Next step, consider 100 grams. They are the 100 grams, 85.7 grams and 14.3 grams. Divide by their atomic masses. You divide by 12 and divide by 1. You get 7.142 and 14.3. I don't know why that answer hasn't come through in my PowerPoint. But you can get your calculator out and work that out, and you'll find that that will work out to be 7.142. And then you divide by the smallest. When you divide by the smallest, that becomes 1, that becomes 2, ratio 1 to 2, CH2. So that's the empirical formula. And what did I witter on and on and on about? How is the empirical formula linked? How is it related to the molecular formula? And I said it was a multiple. I said the molecular formula is always a multiple. Like 1 lot of it, or 2 lots of it, or 3 lots of it. But this empirical formula, 1 carbon, 2 hydrogen, CH2. If you have 1 lot of CH2, carbon weighs 12, and hydrogen weighs 1 each. So 12 plus 1 plus 1 is 14. So if the molecule had 1 carbon in, 2 hydrogens, then it would weigh 14. But the question tells you the molecular mass of the compound is 28. Relative molecular mass being 28. The empirical formula CH2. How many of those do you need to get a relative molecular mass of 28? Well, you need 2 lots of them. 1 lot add up to 14. You need 2 lots of them, and they will add up to 28. And you're told it's 28. So 1 lot of CH2 would have a relative molecular mass of 14. And so to get a molecular mass of 28, we need 2 lots of CH2. And 2 lots of CH2, the molecular formula is C2H4. C2H4. That is the third example. I hope you get a flavour of how to do these empirical formula questions, which people find difficult, but they're not. You just got to learn this table way of attempting these questions, and then they become easy. And then you can all do them. Right, okay. Let's stop there.